Let's talk about something called as thermal expansion. Thermal expansion. In this video, we'll first understand what this is, then we'll look at a couple of examples, and then finally, we will try to dig a little bit deeper and understand the reason behind this phenomenon. Okay, so let's begin. What comes to your mind when you hear the word thermal? For me, thermal is something like heat. And expansion means something is getting bigger, right? Expanding, bigger. So we would say getting bigger. So the idea is, if you heat something or you increase its temperature, then it'll expand, it'll get bigger in size. And similarly, if you cool it down, if you were to decrease its temperature, then it'll shrink in size, it'll contract. And most things really do that. I say most because there are some exceptions to it, but most things around us really experience this phenomenon. So let's first take a couple of examples to convince ourselves that this is really happening around us. I think the most common example can be seen in a thermometer. It consists of a glass tube which is filled with some kind of a colored liquid, so we can see that. Usually it's mercury, sometimes they use other stuff as well. And so if you take this thermometer and you hang it in your room, let's say, and if the room gets hotter, then the mercury, the liquid inside, also gets hotter. And as a result, this mercury will expand. Now, as it expands, you will see the level of the mercury rising like this. And similarly, if the room were to get cooler, or maybe you were to put this thermometer in some ice cold water or something, then the mercury would get cooler and it would contract, it would shrink in size. And therefore the level now will start dropping, and again you can see this. And therefore, the clever application is just by looking at the level of the mercury, you can sort of understand the temperature of the surrounding. Another example can be seen in this picture. Take a very good look at this picture. Can you see something weird over here? The railway tracks have buckled sidewards. What do you think has happened over here? Well, my guess is that this may have been an extremely hot day, due to which the tracks expanded a lot. But there is no room to expand along the length over here. And it's for that reason the tracks ended up expanding towards the side. And this is extremely bad. This is very dangerous for the trains. And so engineers have to take care of this. So what do you think they do? Well, if you have ever taken a walk along a railway track, you may have noticed that there are some gaps left in between. These gaps are left just to make sure this doesn't happen, so that just in case if the temperature goes very high and if the tracks expand a lot, then they can just expand into this gap and not sidewards, and this buckling can be avoided. So again, another example that we can relate to in our daily life. And there are plenty of other very interesting examples, and I really encourage you to explore them by going over the internet or discussing with your friends and teachers. But now for the rest of the video, let's try and dig a little bit deeper and find out what's the cause for this thermal expansion. Why do things expand on heating and they contract on cooling? Alright, let's figure this out using an example. Imagine we have a metallic bar with us. Let's say we have gold. Yeah, we'll assume that someone gifted us this big gold bar, and we're going to use this to understand the secret of thermal expansion. Now, to find out the secret, to figure out the secret, we have to look into the microscopic picture of matter. So imagine we zoom in, this is a magnifying glass. So if you zoom in a lot, what would we see? Well, recall that all matter is made up of atoms. So we would probably see gold atoms. So maybe something like this. And our gold bar is sitting on our table right now at room temperature. So the temperature is, say, 27 degrees Celsius. And so what are these atoms doing at room temperature? Are they at rest? Well, it turns out that they're not at rest. They're sort of like vibrating. They're sort of jiggling around. They're pretty much localized, but they do jiggle a bit. Okay, all atoms are doing that. And it's for this reason we will see that if you pick any two atoms, so let's say you pick these two neighboring atoms, the distance between them keeps changing. Sometimes they come close to each other, sometimes they go farther away. And we can simplify this by assuming that the atoms are fixed at some average distance between them. So even if the distance between them is changing and the atoms are vibrating, we'll assume that they're at rest, they're fixed at some average distance apart. And so now the big question is, what happens when we increase this temperature? What will happen if we increase this temperature? Well, if we do that, then the atoms jiggle even more. So the atoms will, so imagine this is the vibration at 27 degrees Celsius. As we heat it up, as we heat up our gold bar, we will see that the atoms of the gold bar end up vibrating more rigorously, right? All atoms do that, and as a result, what we will find is that all the atoms end up going farther away from each other. The average distance between them starts increasing. Let me just write that down, all right? So when temperature increases, we will see that the atoms vibrate more. Atoms vibrate more. They get more kinetic energy, and as a result, the average distance between them also increases. And it's for that reason, if we were to heat this up, then we would see probably something like this. The same atoms would now be much farther apart. So one would be here, one would be like this. They would be all much farther apart. And you may be wondering, well, why is it that if the atoms vibrate more, that the average distance must increase? And that would be a good question, but that turns out to be a little bit more complicated. It's really interesting, but it turns out to be a little bit more complicated, and so that deserves a separate video all by itself. So maybe we'll look at that in another video, but over here, we're just going to accept the fact that if the atoms vibrate more, then their average distance increases. And from this, we can pretty much conclude what's going to happen. If all the atoms go farther away from each other, and that's the key to understanding this, if all the atoms go farther away, then they end up occupying more space, and the whole gold bar, the material as a whole, will end up expanding. And that's really what's going on over here. So let me just keep that somewhere over here. All right, so that's the true reason for thermal expansion, because the atoms vibrate more and they start going farther away from each other. And we can also see now what happens when you cool this gold bar. If you were to cool this thing down, then the atoms get less kinetic energy, they vibrate less, and as a result, they come closer to each other, occupying less space, and so the whole material ends up contracting. And so this is the secret behind thermal expansion. All right. So let's now look at a classic question that's usually asked when it comes to thermal expansion. And it goes something like this. Imagine we have some kind of a material. So let's say we have some kind of a metallic sheet over here. So this is some metallic sheet at some temperature. And let's imagine we punch out a hole from it. So imagine we take a nice circular hole and we punch it out. And suppose we heat this thing up. We heat it up. Heat it. The question now is, what's going to happen to this hole? As the material expands due to increase in temperature, do you think the hole gets bigger in size, or do you think the hole will get smaller in size? I want you to really pause this video for a while and think about this, come up with an explanation in your head as to what's going to happen. All right? Okay, let me tell you the most common misconception over here. We may think that as the material expands in all directions, as the material expands this way in all directions, the whole thing could also expand into the hole, and therefore the hole size would get smaller. Something like this. But guess what? That's wrong. That cannot happen. And a very easy way to think about this is we go back and we remember that as temperature increases, remember over here, as temperature increases, the average distance between all the atoms end up increasing. And so if we pick if we pick a couple of atoms over here, let's say one over here and one over here, the average distance between them should increase when the material expands. But if the material expands into the hole, or if the hole size shrinks, then we would see that the atoms have come closer to each other, and that's not possible. We just discussed that. And as a result of this, we could now conclude that if all atoms go farther away, then the only way that can happen is that the hole size should increase. And this is very important, right? So the hole gets bigger. You just write that. Hole gets bigger. And let me tell you the best way to think about this. The best way I like to think about thermal expansion in most cases is just imagine that we take a photo and we just stretch it like this. Just stretch it. And when you stretch a photo, you can clearly see that everything inside the photo becomes bigger, including that hole. All right? So don't fall into that trap of thinking that the hole gets smaller in size.